We ended last class with this slide, dealing with what's called the octet rule. The octet rule is basically stating that a full outer shell of electrons is the most stable configuration. So on the worksheet that you just did, when I gave things charges, either positive or negative, I didn't make up random charges. I made up charges that would in fact exist for those particular elements based upon, in large part, this octet rule, this idea of stability. So to remind you about that, we had you draw out the orbital notation for sodium and chlorine. And I'll quickly remind you of what that was for each. So for sodium, this was its orbital notation. For chlorine, it's a little bit bigger. This was its orbital notation. And what we should have noticed from last class is that sodium, if it loses this electron right here, would have its new outer shell at the octet, 8 electrons. Chlorine, on the other hand, needs to gain an electron, because then its outer shell would have 8 electrons as well. And what happens is that sodium loses its electron to chlorine. When sodium loses an electron, it now is a positive charge. So that's why once it loses that one, it becomes Na+. When chlorine gains an electron, it now has a negative charge. It's Cl-. What we went over last class is that an ionic bond is an attraction between a positive ion, remember what that positive ion is called, cation, and the negative ion, the anion. So that's what allows them to kind of stick together, as it says in bold on your note sheet, because I believe everyone has written down 8A and B of the orbital notation. But then in bold it says electron transfer makes both elements more stable because they're at the octet. They stick together due to opposite charges. So, if we go back to our slides then, hopefully that reminds you of what we did last class. And actually, you were one of my classes that was a little bit further ahead than the others. We have 3 questions still on our note sheet. The first one, why does sodium under normal circumstances only have a +1 charge? So in other words, why wouldn't sodium ever lose 2 electrons? What would happen if it lost 2 electrons with its electron configuration? Would it be at the octet? No. Would it gain an electron? If it gains, it's actually getting further away from what its goal is going to be. So when I look at that number 9, I'm wanting you to recognize that really it's not just sodium. It's anything in this first column. When they lose 1 electron, they lose their 1 valence, they're now like a noble gas. I mean, that's the key for anything in that column. Second question of why does chlorine only have a -1 charge? Well, again, chlorine is 1 step away from being like a noble gas with a full outer shell. So any of these halogens on here, if they gain 1 electron, they now have a full outer shell. This octet rule is a rule of stability. The idea that when you have a full outer shell of electrons, thinking back to orbital notation, I think is the best way to demonstrate this. When you have a full outer shell, you are stable. Remember last time in the notes I just mentioned for families, alkali metals don't exist on their own in nature. So you never find pure potassium on its own. You don't find pure potassium on its own because it's more stable when it loses one electron. Very last question on your note sheet says, would this hold true for other main group elements? So for example, what charge would P, phosphorus, have? Again, when I make worksheets, I don't make up random charges. If the goal is the octet makes you stable, how does phosphorus get to the octet? Does it gain or lose? What's easiest? What's less steps? Gaining. And how many would it gain? 3. So phosphorus, for example, would have a -3 charge. That would hold true for nitrogen, which is right above it on the periodic table as well. And this leads us into having our periodic table and writing on it again. Once we have identified that stability is achieved through 8 outer shell electrons, we can now remind ourselves of what the most common charges of these things would be. So for example, I got Evan back here. +1 charge is what I want you to write above your first column. Now hydrogen this kind of excludes, but again, hydrogen's a non-metal. But your alkali metals, lithium on down to francium, are all more stable with a +1 charge. Alkaline earth metals, right, +2 charge. So let's write a big +2 above beryllium. Again, boron is kind of an exception to this, but how about above boron, we'd write a +3. Now I'm going to leave above carbon alone. Because carbon could be a +4, loses 4 electrons, but it can also be a what? Justin?
-4.
A -4. Carbon is kind of smack dab in the middle of, it could take 4 steps this way, 4 steps that way to achieve stability. Same with silicon then. Because carbon is kind of unusual in that 4 steps, I'm going to leave that blank. Because what you're going to find is carbon actually doesn't do ions very well. In our next unit, we're going to go over what's called covalent bonding. That's what carbon does more of. However, directly above nitrogen, just like we said before with phosphorus, let's write a big -3. Above oxygen, a -2. And above fluorine, a -1. Notice that we're not writing anything above the transition metals, the metals in the middle of the periodic table, because they sometimes have to take like 8 steps in order to get to the octet. They usually achieve different ways of stability, like half-filled orbitals and things like that. So because the transition metals are a little goofy, we're going to save that for a future class period. Actually, next class we're going to go over that a little bit more. Why we write these charges up here is they help you see what is the most stable version of that element. Notice that we did not write a charge above the noble gas column, because noble gases already have a full outer shell. They already are stable. So one reason that we do this is to demonstrate what these ions are, to demonstrate that stability of the octet rule. The second reason why we go over this is to deal with chemical naming. And that's our first goal of the day. So this first 5 minutes was just to wrap up what we didn't get to last class. Our goals today is start to learn how to name these compounds when they come together. Okay? So, first sheet I want you to have out would be the one that was titled Binary Nomenclature Type 1 Ionic. So take a minute to get out that sheet that you picked up on the way in. On that sheet, you'll see a list of about 7 sample problems in the middle. I wrote down the first 3 compounds here on the board. What we have to learn to do today is 2 parts dealing with chemical formulas. Now we're not dealing with individual atoms, we're dealing with compounds. More than one atom coming together to form something. We have to be able to look at the formula for something and write down its name. Just like NaCl, sodium chloride, we have to do that with any ionic compound that we're seeing today. So if that's goal number 1, on your sheet, I have the 3 rules in order to name a formula. Rule number 1 says you are naming a metal with a non-metal. Recall last class period, we highlighted a staircase separating out the metals, everything to the left, excluding hydrogen, and the non-metals to the right. So first off, let's make sure we have the right things. Secondly, rule 2 says name the cation, the metal, first. Do not change the name of the element. Rule number 3, write the anion, the non-metal, second. Keep the beginning of the element's name and replace the ending with I. So for example, if I were to write down the name of CaCl2, it'd be calcium chloride. So we don't call it calcium chlorine. By calling it calcium chloride, we're indicating that it's bonded to something else. That's the importance of the "ide" ending. Second one then, barium. So just name the cation, the metal. S is sulfur, but we're not going to call it barium sulfur. We're going to call it barium sulfide. CS is cesium. But we don't call it cesium nitrogen. Usually we just do the first syllable is pretty common, so it's cesium nitride. Take a minute or two right now to answer the other 4 on here on your own. Okay. I have 2 examples from that list up on the board right now. Sodium chloride and calcium chloride. Notice not only the element difference, but the difference between the 2 is how their formula is written. Sodium chloride is 1 Na for 1 Cl. Calcium chloride is 1 Ca for 2 Cls. So that subscript, that lower number there after the Cl, represents that I have 2 Cls in that compound. Some ionic compounds are a 1-to-1 ratio, like sodium chloride. Some are not, like the calcium chloride. What we have to go over is the reason why that is what it is. And to me, one of the easiest ways to go over that is to remind you back of electron configuration. So let's do shorthand here for calcium. What is that? Argon and 4s2. Chlorine is going to be neon. 3s2, 3p5. And there's 2 chlorines, so let's just write it one more time. Neon, 3s2, 3p5. Last class, I introduced to you what an ionic compound was and what an ionic bond was. An ionic bond is between a metal and a non-metal. We have that in both instances up here. An ionic bond is where one element gives electrons to another, and then they both have charges now. One is a positive, one's a negative, and those charges allow them to stick together. That's what's the bond. It's an electron transfer. Why do things transfer electrons? The octet rule. It's more stable to have a full outer shell. For example, chlorine is 1 electron shy of being 3s2, 3p6. So what can happen is calcium can give an electron. But if calcium chloride was just CaCl and calcium gave 1 electron, it still would not be at the octet. it would end in 4s1. We okay with that? So, if calcium lost 1 electron to chlorine, remember sodium lost 1 electron to chlorine? If calcium did the same thing, it would still have 1 electron remaining, and this would become 6. So this chlorine, oh, that's stable, good. But this calcium would still need to lose 1 more electron. And that's why there's a second chlorine in that compound. Because now it can lose that second electron here. And once it does, it's now at the octet. Similar to when sodium loses an electron, it's at the octet. So when you have alkaline metals, they only have to lose 1. But alkaline earth have to lose 2. So now, this needed to give 2 electrons away. There's 2 of them there. That is kind of almost a conservation of mass. However many electrons gained is lost is a way to think about this. Ladies and gentlemen, there's a simpler way to think about this. When you know it's calcium and chlorine involved, what charge would calcium have if it were stable? We just wrote this in the top of the column for calcium. What is it? +2, right? We wrote a big +2 above the second column. Calcium is most stable as a +2. Now that means it loses 2 electrons like I was trying to say there. However, let's just deal with the charges. Chlorine. What charge would chlorine have in its most stable configuration? -1. In an ionic compound, charges balance out because the number of electrons gained have to balance out with the number of electrons lost. 1 + 2 and 1 - 1 do not balance out. We would need 2 of these in order for it to balance out. So if you don't want to think about electrons balancing, you don't have to. I had you write the charges on top of the columns for a reason. You can now just think about charges balancing out to make an ionic compound that is neutral. Because overall, these compounds will have no net charge. Now, I'll give you one other way to think about this. This doesn't work every time, but it typically works. If you write down the charges for your metal and non-metal, then take the number part, and we call it cross and drop. Take the 2, make it the subscript for the other element. Take the 1, make it the subscript for the other element. However, we don't have to write a 1, it's assumed to be 1. That cross and drop method also will give you the formula. An ionic compound, however, is in the lowest ratio of metal to non-metal. So, for example, if this was a 4 and a 2, we would call it a 2 and a 1 instead. Now, that is trying to explain why these formulas are what they are. What we kind of do is practice this a little bit. And the first way I want to practice this is I've written 4 names up on the board. Here's what you're going to do to try to figure out the formula. Step 1, write down the symbol for each element and its charge. Then step 2, figure out what the formula is going to be. You could do that by cross and drop. You could do that by how many of these has to balance out with how many of those. Whatever method you want to choose is fine. But identify the symbol and the charge in order to figure out the formulas. Okay. Hopefully you identified that potassium is a +1 and oxygen is a -2. So if we did that, Connor, way back there now, what would be the formula of potassium oxide? No, potassium oxide, the first one. Now remember, it's cross and drop. So it should be K2O. You need 2 +1s to balance out the 1 - 2. Now in aluminum fluoride, aluminum is a +3 and fluorine is a -1. So Caden, what's the formula for aluminum fluoride? AlF3. Now this is also getting to the point where we have to make sure lowercase and uppercase jive with what's on the periodic table. And what I mean by that is some students, when I walk around checking their work at times, they don't pay attention to the uppercase, lowercase. When we start getting into compounds, we have to pay attention to that. Because capital P, capital B would be phosphorus and boron. Capital P, lowercase b would be lead. So we have to make sure that simple little details like that we abide to. Barium nitride. Barium was a +2. Nitrogen's a -3. Now in this particular one, I would probably do more of the cross and drop method. Take the charge, make it the subscript for the other thing. Because the first two I thought was a little bit easier. A +1 needs 2 of those. A -1 needs 3 of those. So, Andrew, barium nitride, what's the formula? Ba3N2. And that brings us to the last one. Beryllium selenide. Beryllium is a +2. Selenium is a -2. What do you think, Alan? Now we could do, to start off with, Be2Se2. That's doing the cross and drop method. However, an ionic compound is the lowest ratio of metal to non-metal. How did this become a +2 charge? It lost 2 electrons. How did this become a -2 electron charge? It gained 2 electrons. Do I really need 2 of each to make that work? No. So the correct answer for this would be BeSe. Some students do the cross and drop, but then they will divide if there's something that they can divide by both. All right, here we go. If we know how to name compounds and give their formulas, we can then combine this with mole conversions. Now recall, your quiz today will have mole conversions for individual elements, not for compounds. So my hope is this is a little bit of review for the quiz. I realize this is harder than what you're going to be doing on the quiz. But instead of reading that top paragraph, I want to do the first practice problem here right away. The question says, calculate the number of grams of 2.43 times 10 to the 22nd molecules of magnesium fluoride. By the way, there is an asterisk next to molecules because on the very bottom of your page, it says the term molecule is typically used for things that are covalently bonded together, not ionically. However, we will still use the term molecule describing ionic things. Molecule, in terms of mole conversions, is just like atoms. It's the tiny things that we need a ridiculous number of them for, hence the 10 to the 22nd power. So in this question, it's asking for grams, and it's given me molecules. First thing I'm going to do is just like what you would do is if you were given atoms. You're going to convert from atoms, or molecules in this case, into moles. So 2.43 times 10 to the 22nd molecules and I'm going to convert to moles using Avogadro's number. By the way, Avogadro's number is going to be given to you today for the test. I wrote it up on the whiteboard, so you do get to use that. 3 significant digits should be used when doing this. So there's 3 sig digs, right? No, because that 0 to start off with isn't actually significant. So now there's 3 sig digs, right? No, because you don't start counting sig digs till you hit your first non-zero. 4, 0, 4 moles. Now, what makes this type of mole conversion a little more complicated than what you did is what I'm stating for letter B. The molar mass. It says you need to find the molar mass of magnesium fluoride. To do this, you must first figure out the formula for the compound, then use the atomic mass values from the periodic table. Magnesium fluoride. Okay, do we have our periodic table out in front of us? Morgan, what is the symbol and charge for magnesium?
Mg plus 2.
Max, fluorine.
F minus 1.
F is a minus 1. All right, Jenna. What would be the formula for magnesium fluoride then, if it's a plus 2 and a minus 1? Can we do the cross and drop, or how many of these do I need to balance with how many of those? Not sure, Joey?
MgF2.
Yeah, we need 2 fluorines. So MgF2. The reason why we need to know that formula unit is to find the molar mass. I have 1 magnesium and 2 fluorines to take part of that. Justin, look at your periodic table. What's the mass of magnesium? Again, we typically go to the hundredths place.
24.31.
24.31. Lily, how about fluorine?
19.00.
And there's 2 of them in the formula. So I'm going to multiply that by 2. If I add those 2 values together, that gets me the molar mass. That's how many grams per mole magnesium fluoride is. Okay? Part C says use the molar mass to convert moles to grams. If you recall, we had 0.040 moles of our magnesium fluoride. If I want to convert to grams, grams is on the top of my conversion. What's the number that I put in front of the word mole? 1, every single time. That gram value is what you just figured out from the periodic table, 62.31. Multiplying that, keeping 3 sig digs, I get 2.52 grams of my magnesium fluoride. Now, I just showed this to you in 2 separate steps. You could just as easily do this as, 1 conversion, then 2nd conversion right away afterwards. That's completely up to you of how you want to approach this. We don't have a lot of time for practice. We have about 5 or 6 minutes that if you want to get up, practice a little bit, or just kind of shake things out, you can. This sheet is front and back. There's a ton of problems on here. Let's see if we can do 2 problems on here right now, numbers 2 and 3. Okay, take a few minutes, work on that.